In this video, I'll be doing two application problems with linear functions. So let's go ahead and get started. It says here a fax machine was purchased for $625. If the fax machine depreciates $25 each month, then we're going to write a function that gives the value of the fax machine t months after it is purchased. And B, we're going to use the function to find the value of the fax machine after 1 year. All right, so first of all, so it's value that we're going to measure here. We're supposed to find the value of the fax machine. So I think I'll use V for value, and T is going to be it's going to be our time in months. And so I'm going to go ahead and write V of t. Now notice t is the input and V of t represents the value at time t. And so this equals 625. Now depreciates $25 each month means its value goes down $25 each month, where t is the number of months since the purchase. And so we're going to say minus 25t. So if it were 1 month, it would be worth, after 1 month of the purchase, or since the purchase, you would have a value of 625 minus 1 times 25, or just minus 25, it'd be worth $600. V of 2 would be the value after 2 months, so that'd be 625 minus 25 times 2, or minus 50. So you can see that's going to work. So it's important to make sense out of your function. Make sure that it's working the way you expect it to. Now the other thing I'd mention here, I like the way this order is just because its value started at 625 and it's decreasing $25 per month. So logically I like this arrangement, but some people would write it this way and put it in slope-intercept form. So either way, really, I don't think it matters that much. So part B, we're supposed to find the value of the the fax machine after 1 year. Well, first of all, 1 year is 12 months. Remember, time is in months. And so we need to find V of 12. And so I'll go ahead and write a shell for the function, and let's plug in 12. And when you simplify the right side, you get 325. And so it's worth $325 a year later. All right, so let's move on to the next problem here. Whoops, I got a little bit ahead of myself there. So it says here in 1930, the record for the 400-meter run was 46.8 seconds. In 1970, it was 43.8 seconds. Let R of t equal the record, so R would stand for record, in the 400-meter run, and t equal the number of years since 1930. And so as you look at this expression R of t, that's just the record after time t. So that's the idea. With functions, you have this dependent relationship. The record is dependent on how many years have passed, or what the time is. So basically what we have here is two data points. We're trying to write a linear function. Well, we know that a line goes through 2 points, or we can use 2 points to find the equation of a line. And in fact, we have 2 data points here. The first one, let's see, it says in 1930, the record was 46.8. Now keep in mind, t is the number of years since 1930. And so in 1930, how many years have passed since 1930? 0. And so that'll be the point 0, 46.8. I don't know why it's going ahead on me like that. All right, so that's our first data point. 0 represents 1930. That's the number of years since 1930. And 46.8 is the record in that year. All right, or after that amount of time. And then our other point, it says in 1970, well, that's 40 years since 1930, so our t-value will be 40, and our record is 43.8, and so we have the point 40, 43.8. All right, so now we can find our linear equation. We actually wrote equations of lines if we were given 2 points previously, so we're going to do the same kind of thing here. So we're going to need the point-slope form. That's what we use to write the equation of a line. But notice here we have 2 points, and with point-slope form, I need the slope and 1 point. So let's go ahead and find slope first. That's m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And so we're going to get in the numerator, let's see, our x sub 1, y sub 1, we'll call that our first point. That's 0, 46.8. And x sub 2, y sub 2 will be our second point, 40, 43.8. So let's go ahead and plug in our numbers. We get 43.8 minus 46.8. That's our y sub 2 minus y sub 1. And x sub 2 minus x sub 1, well, 40 minus 0 is just going to be 40. So we're going to end up here with negative 3 over 40. Now think about what that really means. Remember, the numerator stood for seconds, and the denominator stood for time, and it's actually time in years. And so basically, the record has dropped 3 seconds in 40 years. Now, if you divide that, you'll find that it's negative 0.075, or the other way to say that is the record's dropping about 75 thousandths of a second on average per year. So that's the basic idea, but that's our slope. And so now we can use either point. I'm going to go ahead and use the first one, 0, 46.8, and the slope of negative 0.075. So let's go ahead and plug in our numbers. We have y minus 46.8 is equal to our slope, which is negative 0.075, times x minus my x value, which is just 0. And so this will simplify quite easily. On the right, we can just write that as negative 0.075x. So we get y minus 46.8 equals negative 0.075x. We'll add 46.8 to both sides, and we get y is equal to negative 0.075x plus 46.8. Now, we are writing the equation of a linear function. In fact, they called it r of t, and I'm using y here. I didn't want to change my notation because when I use point-slope form, we're using the y notation, but I want to change now since we're ready to write the final answer for the function. Instead of writing y, we're going to write r of t. And notice oops, I actually have an x there. I need to fix that because it's not x. Our independent variable is actually t. Let me fix that. And so we get r of t is equal to negative 0.075t plus 46.8. And so this is the function that basically tells us the record after t years have passed since 1930. All right, so we're supposed to find the, or estimate the record in 2020. So that's part B. So in this case, t is 90 since, it's been 90 years since 1930 when you get to 2020. And so let's just plug 90 into the function. And when you do that, you should get 40.05 seconds. And so based on this model, this linear model, we're expecting the record to be about 40.05 seconds in 2020. In reality, it's actually about 43.03. So this actually is good for us to see, because when you model something with a linear equation over a period of time, it's very possible that at some point that model is no longer valid. So basically what's happened since 1970 is that record hasn't decreased very much. And so it hasn't decreased at the same rate as it was before. All right, so that's the kind of thing you got to watch out for when you do modeling. All right, so that's going to be it for this video.